All right, so we're going to try and put together some more of this unit circle understanding. So we're looking at positions of angles on the unit circle, which is like a circle in a coordinate plane. And so what we're going to look at here is general sine, cosine, tangent, cosecant, secant, and cotangent ratios of angles. So hopefully our goal today is to kind of bring together for you why this tool is even useful, called the unit circle, and how it is actually going to help you remember trig functions. So I just want to remind you first, I'm going to draw something different on this diagram. You don't have to draw it. This is just to give you some reference. So let's say I drew this triangle in the circle, and that this was my angle in here first. First, we're going to deal with a simpler angle. If this is a right triangle, and I'm always looking at a central angle, so remember, that's an angle between my terminal side and basically the x-axis here for it to be a central angle. So when we think sine, we used to think in triangles opposite over hypotenuse. Okay? For cosine, adjacent over hypotenuse. For tangent, opposite over adjacent. And then these were the reciprocals of them. And I'm going to pause here for a second to make a note that a reciprocal is different than an inverse. Okay? Reciprocals mean that we just change the order of the division of the fraction. Okay? Inverse means it completely undoes what the function does. And the reason that I'm making such a big deal about this is the last section of this unit is going to deal with inverses, and I really want you guys to really try and separate in your head and understand a reciprocal is different from an inverse. So these that we're dealing with here are reciprocals, okay, and they're more simplistic in the fact they really just are the ratios in a different order. So that's what we're looking at, okay? Now what we want to do is we want to try to understand this in more than context of a triangle, because all the words that we're using in the ratios here, opposite, hypotenuse, adjacent, those all work for a triangle like I have drawn here. In this green triangle, okay, this would be my opposite of my angle, this would be my adjacent of my angle, and this would be my hypotenuse of my angle, okay? And we understand that in a right triangle, okay? And then if I take this picture and I look at this other angle drawn on it behind it that you guys see on your paper, when you outline that angle, do you guys see there's no way to make a right triangle out of that angle? So these ratios that you've written over here, if I want to find the sine of this angle that's more than 90 degrees, and you tell me to use opposite over hypotenuse, I'm going to be really confused because I'm trying to think in my head that a hypotenuse is across from a 90-degree angle, but my angle is more than 90 degrees, so it wouldn't be like that. It would kind of go like this way, and then that wouldn't be able to build a triangle because it would have too many degrees. So we have to convert things like opposite, adjacent, and hypotenuse into how we can use those ratios for all angles, even things that are bigger than 90 degrees. Okay, so I want you to notice that we're going to replace some of the names here, and then I'm going to show you why it's okay. First, look at the green picture that I've drawn, and I want you to realize what the opposite, adjacent, and hypotenuse are in that picture. That the opposite side of the triangle is the same as the y coordinate that we used to get to that point. That the adjacent side of the triangle would be the same as the x coordinate that we used to get up here to that point on the circle. And that the hypotenuse would be the same thing as the radius of the circle, okay? So my hypothesis, so to speak, is that we can replace opposite with a y coordinate, adjacent with an x coordinate, and the hypotenuse with the word radius in this position, okay? Now, why your drawing doesn't look like that is because you guys understand that for a basic right triangle, and we want to show you why this is important when we go beyond 90 degrees. So when you see this angle here, this angle lands with its terminal side over here. We would not build the triangle by connecting the initial and terminal side. If we wanted to build a right triangle at this position, we would connect it down to the x-axis here. And so we'd actually build the triangle around this angle in here. This angle is not the same as this angle, okay? This one in here we would call the reference angle. And let me give you guys a picture of that on your unit circle. When you look back there, remember how we drew this triangle over here? And we said this 30 degrees was the same as this one here, and see how these coordinates ended up being the same as these ones over here, just with some difference, negatives and positives. So even though when we look at the picture we're currently on, we know that this angle is a lot bigger than this one right here, we can use the reference angle to build the triangle, and then we would still have opposite, adjacent, and hypotenuse, and notice that the opposite would still be the y coordinate at that position, the adjacent would still be the x coordinate to get to that position, and the hypotenuse would still be the radius of the circle. Okay? So we're going to write these ratios that you've always known, your SOHCAHTOA, we're going to write them in a different way. Instead of using opposite over hypotenuse for sine, you can still use that, but you could also use the y coordinate divided by the x coordinate, because the y coordinate is the opposite and the x coordinate is the adjacent. And the hypotenuse is the radius. So opposite would be y coordinate, and I'm sorry, I think I misspoke previously. The hypotenuse would be the radius. So sine could be O over H, like opposite over hypotenuse, but we could also think of it as y over r in a picture like this, where it's the y coordinate divided by the radius of the circle. That means the cosine adjacent over hypotenuse can now be thought of as x over r, and tangent opposite over adjacent could be thought of as y over x. Okay? And then same with their reciprocals. So we'd have r over y, r over x, and x over y. For the unit circle, now remember, if we're using the unit circle specifically has a radius of 1. And this is why mathematicians chose the unit circle. And after spring break, we'll show you that they were allowed to choose it, that it's okay for them to choose just this one. But if we take the sine ratio of y over r, but we know now that the radius is 1 and we replace the radius with 1, y divided by 1 is just y. Cosine would then be x over r, which is like x over 1, which would then work out to just be x, and tangent is still y over x, and none of those get replaced. Okay? And then these would be the reciprocals of those. So 1 over y, 1 over x, and x over y. Right? So why is this such a big deal? This is where that unit circle can be like a multiplication table for you, that it can be a tool that simply tells you very quickly, if you understand how it's put together, certain things. So right here it says the sine of an angle. So when someone writes sine of an angle, okay, on a unit circle is the same as the, so I'm looking right here, the sine of an angle on the unit circle is the same as the y coordinate at that position. Where the cosine of an angle, when someone asks me for cosine of something, on the unit circle, it's going to be the x coordinate. And when somebody asks me for the tangent of an angle, on the unit circle, it's the same as the y coordinate being divided by the x coordinate. Okay, so that kind of gives you a summary of what's happening here. So we're going to use this to fill in some ratios on the next page. So I'm going to help you fill in part of the chart, and then I'm going to have you guys do the rest for homework, and the beginning of our notes next time we'll check the chart. So when you look at the ratio chart, it has different columns, so I'm going to go through what they mean. So it has the degrees, the position that you're looking at on the unit circle. It also has the angle in radians. We are going to do this. This is going to be something that we do later. Okay, we're going to come back after break and talk about the angle positions in radians. Okay. Then it asks for the coordinates. So let's say I'm doing the 30-degree angle. And again, your goal is to have those coordinates memorized. If you know your special right triangles, it's not too bad. So when I look at the unit circle, At the 30-degree position, these are the coordinates right here. Rad 3 over 2, 1/2. So back in my ratio chart, I'm going to put rad 3 over 2, 1/2. Those are the x and y coordinates at that 30-degree position. And then remember what we just went through in our chart. We used to think of sine as opposite over hypotenuse. These are unit circle ratios, and now we know that in the unit circle, we can think of the sine of an angle as the y coordinate. So this means if I was calculating the sine of the angle, which in this case is 30, I would use the y coordinate, which would be 1/2. So I know here that the sine of 30 equals 1/2, because that's the y coordinate from the coordinates at that angle position. The cosine of 30 is going to equal the x coordinate, which is rad 3 over 2. And the tangent of 30 is going to be the y coordinate divided by the x coordinate. And you might have to do this off on the side. So we have 1/2 divided by rad 3 over 2. So that would be 1/2 times the reciprocal of rad 3 over 2. So that would give us 1 over rad 3. And again, we don't leave the radical in the denominator because we're trying to write a rational expression. We get rational denominator, rad 3 over 3 as our tangent. Okay? The cosecant is going to be 1 over y, or the reciprocal of the y coordinate, or the cosecant is the reciprocal of the sine. So you already calculated the sine, it was 1/2. So the cosecant will be 2 because the reciprocal of 1/2 will be 2 over 1. The secant is the reciprocal of the cosine, so that will be 2 over rad 3. But again, we want to rationalize that denominator by multiplying by 1 in the form of rad 3 over rad 3, and we get 2 rad 3 over 3. Okay, and that was the reciprocal of our x coordinate. And our cotangent is going to be the x divided by the y. So you have a couple of options here. You can take what you already got and use the reciprocal, or you can redo the division if you want. You could do rad 3 over 2 divided by 1/2, which would be rad 3 over 2 times the reciprocal of 1/2, which would be rad 3. And then let's say I'm going to do one more of these for you, and then I want you guys to go ahead and try and do the others. And then, like I said, we'll check that on the next day's video notes. So I'm going to go ahead, and the other one I'm going to do for you. So I did 30 degrees, and now I'm going to go ahead and do 90 degrees. So look back at your unit circle at 90 degrees, or again, the goal is to have memorized the coordinates at each of these positions. At 90 degrees, our coordinates are 0, 1. So I'm going to write those down. And that's enough information about the 90-degree position for me to do all of the trig calculations. So sine of 90 degrees would be the y coordinate at that angle, which is 1. Cosine of 90 degrees would be the x coordinate at that angle, which is 0. The tangent at 90 degrees would be the y divided by the x. That would be 1 divided by 0, which is undefined. The cosecant is the reciprocal of the sine. So 1's reciprocal is still 1. The secant is the reciprocal of the cosine. So you had 0. When you flip 0 over, it would look like 1 over 0, which again is undefined. And then the cotangent is x divided by y. So x divided by y would be 0 divided by 1, which is 0. So I'm going to stop this video here, and then you guys are going to try and do the rest of the coordinates yourself for this, and then you can check it on the next video notes.